We explained the meaning of order before of any function. Now is the time to define it mathematically. So we call it big O. That stands for order. So it says, suppose you have two functions, f and g, both of them from set of integers or real numbers to set of real numbers. We say that O of x is of order of g of x, denoted by f of x belongs to O of g of x, if and only if there are two constants c and k satisfy this inequality. So this inequality consists of two functions f of x and consists of two constants c and k in addition to the variable of the function as x. Let us go back to our early example, the introduction example, and show that what we have reached was exactly the same as this definition. In this example, we have concluded that 5n squared was less than or equal to half n cubed for all n greater than 10. The basic definition for big O states that f of x, the absolute value, is less than c, the absolute value of g of x, for all x greater than k. Now, if you match the definition for big O with our example, where are the components of this definition in our example? First, f of x is 5n squared, c is half, and g of x is n raised to power 3, and k is equal to 10. So here we have the constant c, this is the constant c, and here we have the value of k as a constant in the definition. So here we can write by saying that 5n squared belongs to big O of n raised to power 3. So to prove this relationship, then you need to satisfy this inequality by finding two constants. Remember that the order of n raised to power 3 are all functions that do not grow faster than n raised to power 3, and 5n squared is one of them. This relationship is also can be represented graphically. Now, if the x-axis is for the variable x, and as what we did before, notice that the blue color graph is for c of g of x, and the black color for f of x. Since f of x grows no faster than g of x, so after x greater than k, then f of x is always in lower level than g of x multiplied by a constant. Even if you try to change the constant for smaller values, in this case you are increasing the value of k. At any certain point, f of x, when x goes to infinity, will be always less than of c of g of x. And we say that f of x is big O of g of x. The constants c and k are called witnesses to the relationship. And these witnesses are not unique, so we need only one pair of witnesses to establish this relationship. Let me show you an example. The example we presented in the introduction, we showed that 5n squared was less than or equal to half n raised to power 3 for all n greater than 10. According to the basic definition, that 5n squared belongs to big O of n raised to power 3, and the witnesses we have, this is the value of c and this is the value of k, and the witnesses we have, c is equal to half and k is equal to 10. And we will label these two values as our first witnesses. Now we will replace the constant 0.5 by 0.1, and our relationship or the inequality becomes 5n squared less than or equal to 0.1 n raised to power 3 for all n now greater than 50. It's not greater than 10 anymore, and you can prove it by drawing the graph of these two functions. Now, according again to the basic definition of big O, we have 5n squared belongs to big O of n raised to power 3, which is the same as this relationship we have obtained earlier, but we have different constants. Now this time the value of C is 0.1 and the value of K is equal to 50. So we say that C is equal to 0.1 and K is equal to 50. And again, we have obtained different witnesses for the same relationship, and we will label them witnesses number 2. This example shows that if we have an order between any two functions and you would like to prove this order by using the basic definition, then it is not necessarily that the constants you obtained in the definition are unique. Most of our functions that we are going to deal are positive functions, especially functions for the analysis of algorithm, which represent the running time of an algorithm, and we know that the running time is always positive. So for simplicity, we will simplify the inequality by ignoring the absolute value, and the inequality condition can be simplified as f of x less than or equal to c multiply of g of x for all x greater than k. We have already mentioned that for every value x greater than k, if the relationship between f of x and g of x is equal to this, then we say that f of x is big O of g of x. Or we can say f of x is of order of g of x. And this is how we can describe the relationship between g of x and f of x. It says that as x increases, f of x grows no faster than g of x. That means O of x can never go above the curve for g of x. In other words, we say that g of x is an asymptotic upper bound. When we say asymptotic, it means approximately. So they don't reach each other. Maybe they are not equal, but they will go close to each other. This is like finding a limit in calculus. So we say that g of x is an upper bound for g of x. For functions that their input is n, is usually for positive input, and for x is used for real number x. So whenever we are going to deal with functions with positive input, we will label them fn, and for real number input, we will label them f of x. So let's come back to the definition again of big O, now mathematically. Now we need to involve the definition, the basic definition of big O, and the meaning of order. We explained it before, but we assume that we know the relationship between functions, and any function grows no faster than another function. We say it belongs to its order. So what does f of n belongs to O of n means? And what is in fact O of n squared? O n squared in fact is a set that consists of a family of functions. Again, I repeat, I say that order of n squared are all functions that grows no faster than n squared. It means when you draw them, they will fall below the curve of n squared. Now, how to involve the basic definition in the order of n squared definition? Here it says O of n squared is equal to a set that the members of those sets are Tn. And what are these Tn? These Tn that satisfies the basic definition, Tn less than or equal to Cn squared, and this is n squared. So any function that is less than or equal to n squared by a constant will be part of this order or set. Here are some examples of Tn that satisfy this inequality by a constant. So we can see the order of n squared as a set represented by Venn diagram. Every member of this Venn diagram or this set is a function, but a functions that satisfy the basic definition, which means less than or equal to n squared by a multiplication of a constant by n squared. So to prove that 3gn plus 8 is big O of n squared, apply the basic definition, find C, and here you have the answer. So the value of C is 11, and so this inequality is satisfied. So we say that 3gn plus 8 is big O of n squared. Also, how to prove 5n plus 7 belongs to big O of n square? Then we need to prove that 5n plus 7 is less than by a constant multiplied by n square, and the proof is here. So the value of c is equal to 12. Similarly, for 2n log n, the value of c is 2. So from these inequalities, we can tell that these three functions belong to order of n squared. Now, any polynomial of degree 2 is also part of the order of n squared. And here are some examples. For example, 6n squared plus 9 is belongs to or is order of n squared, because when you apply the basic definition, this inequality, the value of c is equal to 15. Of course, these constants c are not unique. You can find other values as well, but you need only one. And how to prove that 5n squared plus 2n is big O of n squared? You find a constant which is equal to 7. So O(n squared) is a set that consists of all functions that grows no faster than n squared. Some authors of textbooks, they don't use the symbol belongs to, they use the symbol equal. Although conceptually this is not correct, because f of n generates numbers and O(n squared) is a set. So number equal to a set conceptually is not the same. But equal here is just used as a symbol. So in those textbooks, if you see f of n equal to O(n squared), it is the meaning that f of n belongs to O of n squared. Here is a chart for common functions that appear quite often in the analysis of algorithms, and here is the relationship between them. So this symbol is used for partial order. That means 1 is of order log of n, log of n is of order log n square, and square root of n is order of n, and etc. So if you go from top to bottom, any function on top is of order of the function in below. So this is a constant, logarithm, log squared, and this is root, linear, n log n, quadratic, cubic, quartic, exponential, factorial, and also we can include one more, that it is n raised to power n.